All right, so now we're going to start into cryptography. Some of the main things that we'll talk about in cryptography is going to be public key cryptography, working with PKI or the public key infrastructure. The role of this cryptography is going to be, ensuring this integrity and the authenticity of the data, making sure that we approach with confidentiality and be able to encrypt anything that comes inside of there. So with integrity and authenticity, we're going to deal with data integrity, which guarantees the message was not altered. Any changes in the data that was transit will be detected, and integrity will ensure that the implementation used by either side for the secure hash algorithms, whether that's SHA-2 or SHA-3. You also have MD5 message digest algorithm. It's still in use, but pretty much should be avoided as it's insecure and creates vulnerabilities in the network. It's fairly easy to crack with today's technology, both CPUs and GPUs. Using origin authentication guarantees that the message will not have a forgery and does actually know where it came from or whom it states. Many modern ones ensure authentication and algorithms such as hash-based message authentication code or Hmac. In confidentiality, we're going to make sure that this guarantees only authorized users can read this message. If the message is intercepted, it can't be deciphered within a reasonable amount of time. Data confidentiality is implemented using symmetric and asymmetric encryption algorithms. And then data non-repudiation is guaranteeing that the sender cannot repudiate or refute the validity of the message sent. This relies on the fact that the only sender has the unique characteristics in the signature to be, or for how that should be treated. Most of the time when we're dealing with encryption, almost anything can be broken at some point. The problem usually boils down to is, can you do it within a reasonable amount of time? Early on, you could crack, like I said, MD5. MD5 can be cracked fairly fast now. Even your phones have enough power to really crack MD5 fairly fast. But once you start throwing in things like ASICs or even better using, CPUs, GPUs, which are multi-purpose, but you can also get some ASICs that'll sit out there and just do specific algorithms, and that allows you to crack significantly faster. So the way a hash function works, hashes are used to verify and ensure data integrity. Hashing is usually based on a one-way mathematical function that is relatively easy to compute, but significantly harder to reverse. So as you see in this diagram here, you start with some plain text or data of arbitrary length, run it through a hash function, and you end up with a fixed length hash value. This is usually what's referred to as a digest down here below, or a digital fingerprint. This is what's happening when you're taking a file and therefore running it through a hash. Now, you're not encrypting the file. You're just getting the hash of that file in order to verify data integrity. So if you're on, browsing the internet and downloading files, etc., a lot of times they'll give you an MD5 hash. And that MD5 hash is so that you can run an MD5 against whatever file that you downloaded and find out what the result is. And if that MD5 matches the public hash that's been distributed with that file, then you know that the data integrity is valid. If it does not match that, then those files have been tampered with in some way. So with hash functions, it's done in a computationally and feasibly for both sides of different data to come up with the same hash output. So every time the data is changed or altered, the hash value also changes. And because of this, cryptic hash values are often called digital fingerprints. They can be used to detect duplicate data files, file version changes, or even similar applications. These values are used to guard against accidental or intentional change of data or accidental data corruption. And therefore, the cryptic hash function is applied in many different situations for the entity authentication, data integrity, and data authenticity purposes. So how does that cryptic hash operation work? Generally, this is done mathematically. Given the equation H equals HX, you're going to see how you can operate a particular hash function. So the input's going to be of any length. Output has a fixed length. It always has a given value on the output. So HX is relatively easy to compute for a given X. Whoops. And HX is one way. You cannot reverse it. So typically you cannot, quote, if you get that hash, you can't really crack it back and get the files, if that's what that is implying in that case. So it's always a one way and it's not reversible. The HX is a collision free, meaning that two different input values will result in a different hash value. And so if a hash function is hard to invert, it is considered a one-way hash. And hard to invert means that a given hash has a value of h and computationally infeasible to find an input for x, such as h equals hx. So MD5 and SHA, these hash functions are used to ensure the integrity of a message, either accidentally, changed, whether it's accidentally or intentionally. For example, if I was to send $100 over here to Alex, it gives me a hash and the starting hash. And you'll notice that when it gets over to the other end that you ended up with $1,000 that came out here. They're different hashes when they're sending to different people. So no matter what you're encrypting, even if I send $100 again to Alex, I should not get the same starting hash over here as it goes through. So an MD5 of 128-bit digest, this was was originally developed by Ron Rivest and used in internet applications. MD5 is a one-way function that produces a 128-bit hashed message. MD5 is a legacy algorithm and used only when no better alternatives are available. It's typically recommended that you use SHA-2 or SHA-3 to be used now instead. So SHA-1 was developed by the United States National Security Agency, or the NSA, back in 1995. It was very similar to the MD5 hash functions, except SHA-1 creates a 160-bit hashed message and is slightly slower than MD5. So SHA-1 had some known flaws and is now considered a legacy algorithm. SHA-2 was also developed by the NSA. It includes SHA-224, 256, 384, and 512. Using SHA-2 and then SHA-256, 384, and 512 algorithms should be used. So these are going to be the different bit of messages that are encrypted there. So if you're doing a SHA-256, that's pretty, decently hard to crack, but you get up into 512 in those, and that's significantly harder to go through. And now we have SHA-3, which is the newest hashing algorithm and was introduced by NIST as an alternative to the SHA-2 family of hashing algorithms. SHA-3 includes SHA-3 224, 256, 384, and 512. This SHA-3 family are the next generation algorithms and should be used whenever possible. So for the most part, you could use any one of these clear down to MD5. What really boils down to is the computational cycles that you have available. So if you're running on a real low powered, CPU or something like that, you're not going to be able to get these higher algorithms. And so in order to deal with some of that, what you're seeing is a lot of processors now have coprocessors built onto them for algorithms and things like that. So for example, your Intel processors now have AES hardware decryption directly in the processor. And this speeds things up dramatically when you're dealing with that particular algorithm. That's where, when we start talking about cracking and things like that, with the CPU, you can pretty much crack anything. It's what's considered a general purpose CPU, but it's obviously not optimized for every algorithm. So every code that you put through it, depending on what you're looking to crack with a CPU, you'll get different levels of speeds that you can go through there. And when it comes to CPU, more cores isn't always necessarily better. What generally is going to be better is the speed of that particular processor. And as you know, if you've bought processors in the last 10 years, you can generally get a lot of cores now for a relatively decent price. But if you want those really high speeds, 5 gigahertz plus, you're really going to have to pay an arm and a leg for some of those processors. So while hashing, it can be used to detect accidental changes. It cannot be used to guard against deliberate changes that are made by the threat actor. There is no unique identifying information from the sender in the hashing procedure. That means that anybody can compute a hash for any data as long as it has the correct hash function. And therefore, hashing is vulnerable to man-in-the-middle attacks because it does not provide security on the transmitted data. To provide integrity and origin authentication, something else is required. And so hashing algorithms are only used to protect against accidental changes and does not necessarily protect the data from deliberate changes. So when it talks about origin authentication, this is typically what Hmac is used for. Hmac is just an additional secret key that is input into the hash function. And it can also be known as seeding or salting a particular hash. So Hmac authentication, you're going to take your plain message plus a secret key, run that through a hash function, and then get the output down below here. So now you can not only try to send the data, but if you don't have the right key, you're going to be unable to get the appropriate hash that you have down below here. And so Hmac is calculated by using a cryptic algorithm that combines a cryptic hash function with the secret key. And typically this is done with the Hmac. If the two parties share that secret key and use Hmac functions for authentication, then a properly constructed Hmac digest of the message that a party received indicates that the other party is the originator of the message. And this is because the other party possesses the secret key. So you'll tend to see this during VPNs. If you're encrypting VPNs, you'll use Hmac functions. So to create an Hmac value, as you can see here, they're inputting different length and then that secret key, and then the authenticated digest is then attached to the message and sent on. Go to verify that. You're going to need the secret key. You're going to take the data, run it back through the hash function, and then check this hash and make sure it arrives. If you don't have, you have to have the secret key in order for this to work. So as they're showing here is a Cisco router using Hmac. This is typically for OSPF is what they're showing in this case. But like I said, it's used most often in VPNs is where you'll see it. R1 is using to send a link status update over to R2. So R1 is going to calculate the hash value using the LSU message and this link state over here. And then using the secret key, the resulting hash function is then sent to the LSU on router 2. And then it'll calculate the hash value using the LSU and the secret key. R2 accepts the update if the hash values match. If they don't, then it discards the update. And the idea here is that you can't inject your own routes in the routing table if you don't have this secret key. And so when you configure router 1 and router 2, they must be configured with the same secret key. You will have a lot of labs with this particular module. The other two modules for this week do not have any labs, so it's just this first module and dealing with encryption and cryptography. So you'll work with hashing things out. You should definitely learn that. When it deals with confidentiality, there's two classes of encryption that do this. You have asymmetric and symmetric. Symmetric encryption algorithms are things such as DES, 3DES, and AES, as I mentioned before. And those are based on the premise when the communicating party knows a pre-shared key. Data confidentiality can be ensured using asymmetric algorithms such as Rivas, Shamir, and RSA, and then using a public key infrastructure. And so you can see the two differences between them. Typically with a symmetric key, you're going to use the same key to encrypt and decrypt. They're very short, so it's usually 40 bits to 256. These can go a little bit higher, but 256 is usually the max. Faster than asymmetric encryption here. However, it's commonly used for bulk encryption data like VPN traffic. Asymmetric data, however, is going to use different keys to encrypt and decrypt. Those key lengths are anywhere from 512 bits to 4096 bits. So notice they're significantly longer there. Computationally tasking, therefore slower, and then using symmetric encryption and commonly used for quick data transactions such as HTTPS when accessing your bank data. So the idea is that the data is not incredibly huge here, so that yes, it takes longer to calculate this, but if the data that's being sent isn't very large, then it can still send that through computationally fairly fast. Here, this is going to be your bigger files going through. For symmetric encryption, they're going to use the same shared key, but to encrypt and decrypt. It's also known as the secret key, known as the sender and receiver before any encrypted communications can take place. Again, commonly used for VPNs. All right. It's going to be because symmetric algorithms can use less CPU resources than asymmetric algorithms, as we mentioned. It needs to be fast when using a VPN, and therefore using symmetric encryption algorithms, the longer the key, the longer it will take for somebody to discover the key. So most encryption keys are between 112 and 256. Usually you want to use a minimum of 128 and then use a longer key for more secure communications. Most routers and things like that for firewalls are strong enough computationally that they can handle the 256. And so you can use 256 to keep yourself secure. They're usually classified as either a block cipher or a stream cipher. So on a block cipher, they're usually going to be fixed block plain text, going back to a ciphertext of 64 or 128 bits, as you can see going through here. And common block ciphers include the DES, which is a 64-bit block size, and then AES with a 128-bit block. And then stream ciphers, this is where you're going to send 1 byte or bit at a time. So it's going to just encrypt it like this going across. And these are like a block cipher with a block size of just 1 byte or 1 bit. They're typically faster than block ciphers because the data is continuously encrypted. And examples of this is going to be RC4 or A5, which is used to encrypt GSM cell phone communications. Some well-known encryption algorithms that you can see here. We mentioned these before. I won't go into big details. AES is going to be the main one that you will use. 3DES was the replacement for DES back in the day. You also have Ssl, which is a software optimized encryption algorithm. It is faster than the AES, and it's a stream cipher used at 160-bit encryption key. It has a lower impact on the CPU using everything else. Remember that a lot of CPUs, mostly Intel right now, I'm not sure if AMD has these, but you'll typically see this listed as their features, that it has AES de-encryption, and that's a hardware, which means it basically has an ASIC that's programmed specifically for this algorithm and can decrypt it much faster or encrypt it much faster, either way. So asymmetric encryption, these are typically your public key algorithms. They're used to share things. You'll typically see this for like SSH when you guys are using public key infrastructures for that. The process is also reversible, so the data is encrypted with the public key, requires the private key in order to be decrypted, and then asymmetric algorithms can achieve confidentiality and authenticity by using this process. And so it always consists of 2 different keys. You have a public key and a private key. The public key is just that. It's the one that's sent out to everybody and they have to pull down in order to use it. And then you should have a private key used for the decryption side of things. So data comes in, gets encrypted by the public key, gets sent across. The decryption key is going to be your private key, and then you'll go ahead and bring that back out to plain text. So again, these are typically used between key lengths are between 512 and 4096. Keys greater than or equal to 2048 can be trusted, and therefore, while key lengths of 1024 or shorter are typically considered insufficient. Different protocols that will use this. There's other stages of IPsec VPNs that use an IKE or an internet key exchange. You also have SSL, which is going to be your typical like HTTPS encryption there, using TLS, the transport layer security. As I mentioned before, SSH is really popular with this. Instead of using a username and password, almost everything uses SSL keys now, or SSH keys rather, which uses the public key infrastructure. And then you have this PGP, which is just considered pretty good privacy. And that's a computer program that provides cryptic privacy and authentication. It's typically used in the security of email communications. So there's a bunch of these. You'll hear Diffie-Hellman, which is a pretty common one here, in order to get that through, depending on the key length that you go through. DSS, DSA, RSA is another common one. This is what's used for your public key infrastructure. And so it has different difficulties based on what you choose in between there. EL-GAML, which is kind of based on Diffie-Hellman and that key agreement. The main disadvantage to this is that its encrypted message becomes very big, about twice the size of the original message. And for that reason, it's only used for small messages such as keys. And then you have elliptical curve techniques. This is used to adapt to many cryptography algorithms, such as Diffie-Hellman or Elgamal. The main advantage is the elliptic curve cryptography is that the keys can be much smaller. So you'll notice key length up here is significantly smaller. So for confidentiality, they're used to provide this without a pre-sharing password. Whoops, sorry, I scrolled there. The confidentiality objective of an asymmetric algorithm is initiated once the process started with a public key. And so again, as we talked about before, the public key is used to encrypt, private key is used to decrypt, and that ensures your confidentiality. So if you want to talk about this, Alice will come out and say, can I get your public key from Bob? Bob sends it back as the public key, and then she can go ahead and decrypt that. So Alice uses the public key in order to encrypt messages and things agreed upon, and then sends that encrypted message back over to Bob. Bob is then going to use his private key to decrypt that message. So he basically says, if you're going to send me anything, send it with my public key, and then I use my own private key in order to get that back down there. So once Bob is the only one with the private key, Alice's message can then be decrypted by Bob, and thus confidentiality is achieved. So you're never sending the ability to decrypt the traffic that you're encrypting. You're asking for them to encrypt with your public key. Only you can decrypt it at that point. Okay. This is used for authentication as well. As we talked about, that's really common within SSH these days, especially if you're doing anything on the cloud or virtualization. Almost everything now requires that you have a public key as opposed to a username and password, as it's really hard to break that type of infrastructure. You would have to guess the key or find the key at some point. So for integrity, you're going to see this here. In order to make sure that this message authentication is integrity, it just makes sure that it's not been modified. And so you can go through and decipher that. She'll use the private key to cipher a hash in the message, et cetera, going through. All right. So Diffie-Hellman, again, we talked about this one, is an asymmetric mathematical algorithm, allows two computers to generate an identical shared key without having to ever communicated before. So the new shared key is never actually exchanged between the sender and receiver. The key is used by an encryption algorithm to encrypt traffic between two systems as both parties know it. And therefore, an example of this, again, is typically an IPsec VPNs, and sometimes when SSH data is exchanged as well. So this kind of shows how it works. So you get a agreed upon color, you have a secret color, which gives you a public color. And then you have this for each person that goes on either side. And so when you know this public color and the secret color, you'll end up with the final color. This is just a graphical way of representing that. So DH is going to be very large numbers in its calculations. It's typically using different DH groups in order to determine the strength of the key that's used in the public key arrangement. The higher the group numbers are more secure, but require additional time to compute the key. So if you're sending VPN traffic, every time it takes time to decrypt this data, therefore your throughput is going to drop. You're not going to get 1 gig of traffic going through on a VPN. You would require a significantly powerful firewall or something that's doing the encryption on the far side. And so you can see these Diffie-Hellman groups. Typically group 2 is one of the more common ones that's used. But obviously as you go higher, you're going to see bigger key groups go through there. Cisco supports up to like 19, 20, and 24 on the groups, which are significantly higher. And you guys will do a lab going through encrypting messages with OpenSSL. You'll also have one that'll allow you to create and encrypt files and then recover encrypted zip files as well for passwords. You'll also go through and examine Telnet and SSH and Wireshark in order to see these type of encryptions being used in between those. So for public key cryptography, digital signatures are basically a mathematical technique used to provide authenticity, integrity, and non-repudiation, basically coming back and going through there. The signature is always proof that the document's been signed by the actual person. So when using code signing, this is used for data integrity, authentication purposes. The code signing is used as a verifying the integrity of the executable files downloaded from a vendor website. It also uses a signed digital certificate in order to authenticate and verify the identity of the site that's used to source the files. And then you have digital certificates, which are similar to like a virtual ID card and used to authenticate the identity of a system with the vendor website, and then establish a communicated or encrypted communication connection between the exchange of confidential data. And so we mentioned these different protocols or different algorithms rather. You have DSA, which was the original standard for generating public and private key pairs. You now have RSA, which is another main one that most use, but you can also use a new one called ECDSA. It's a newer variant of the DSA, and it provides a digital signature authentication in order to add benefits of computational inefficiency or efficiency, and small signature sizes and minimal bandwidth. So again, executable files are usually wrapped in a digitally signed envelope, which allows the end user to verify the signature before installing the software. And so anytime you guys have installed newer software on newer operating systems, you're going to have this digitally signed exe or executable file being sent, especially with DLLs, et cetera, within the Windows environment. They're going to have to be digitally signed, which means you have to have a certificate to verify their authenticity. And so like for this, you'll see sign.exe. If you look at the file properties, you can see it was the different files that are go through here, and you can see the different certificate or the digital signatures that come up there. And you can see what algorithm it was encrypted by and the timestamp, et cetera. You can get more details in order to see what happened with that certificate. And then you can view that certificate, see that it was authenticated by Cisco systems, just like a standard certificate that you would have in your web browser. And this one is for doing SHA-2 in order to validate what's going on there. So once this one was become invalidated, then it would not be able to authenticate your exe file. You can kind of follow down that certification path. So these are no simple, are just like, regular certificates that you get. Digital certificates just going to go through by a certificate authority. If you haven't worked with digital certificates before, the way they are is they issue those to a particular individual or a company. They're going to have expiry dates, and you're going to have a certificate authority that is the overall authority for this. And so you'll have different certificate authorities that are out there on the internet, along with different levels of certificate authorities. So the way these are used, you'll have Bob, who is confirming an order for Alice, ordering from the website. They confirm the order, and the computer creates a hash of the confirmation, as you see here. The computer then encrypts that hash with Bob's private key. The encrypted hash, which is a digital signature, is added to the document, send down here, and then that order confirmation is then sent to Alice over the internet. So when Alice receives that signature, she's going to accept the order confirmation with the digital signature and obtain Bob's public key. Alice's computer will then decrypt the signature using Bob's public key, not his private key, but the public key, in order to reveal the assumed hash value of the sending device. And then Alice's computer will generate a hash of the received document without its signature and compares this hash to the decrypted hash. If the hashes match, then the public document is authentic, and therefore it means the confirmation is sent to Bob that it has not changed since it was signed. So from the authorities wise, internet traffic always consists of traffic between two parties, and then establishing an asymmetric connection between two hosts. The hosts will exchange their public key information. And so an SSL certificate is a digital certificate that confirms the identity of a website domain. To implement SSL on a website, the user must purchase an SSL certificate for a domain from an SSL certificate provider. A trusted third party does a prior issuance of credentials, and after this in-depth investigation, not really that in-depth, it basically requires you to authenticate your domain. The third party issues credentials that are difficult to forge. And then when computers attempt to connect over the website over HTTPS, the web browser will check the authenticity of that certificate, make sure it's valid and originated from a reliable certificate authority. Once it validates the website is true, then it will go ahead and save that certificate locally by the web browser and used in subsequent transactions. And therefore, the website's public key is included in that certificate and used to verify future communications between the website and the client. This is just going to take you through. They're doing it with the analogy of using your driver's license and the DMV, but it's very similar with that central authority there. So PKI is usually needed to support large-scale distribution and identification of public encryption keys. The PKI framework facilitates a highly scalable trust relationship, and therefore it consists of hardware, software, people, policies, procedures, etc., that can be used to create, manage, store, distribute, and revoke digital certificates. I'm going to skip through these here. When you're using the authority system, many vendors will provide certificate authority servers as a managed service for an end product. A lot of times you'll see things like Semantic Group or Komodo, GoDaddy, Global Sign, etc. You even have Let's Encrypt out there if you've never used certificates before. Generally, you have to pay for these type of certificates. You have things out there like Let's Encrypt that allows you to do it for free. However, the certificate is only valid for a certain number of days. I believe it's 90 days with Let's Encrypt. So you're having to replace that certificate every 90 days. If you're good with some programming, it's really not that bad to write a small script that will have that go ahead and re-authenticate that for you every 60 days. And therefore you fall within your 90-day renewal that you need to do. There's different classes of these authorities. So for example, class 5 is used for private organizations or maybe even government security. It's trusted much, much more than a lower class certificate. So you can go through on your systems. You can always look at your public keys that go through there or the public certificates. And you can look through your particular browser and typically see these in here as well. So the way the PKI trust system works, if you have a single root PKI, in this case, it's typically called the root certificate authority, and it issues all the certificates to end users within the same organization. The benefit of this approach is simply in simplicity, but it's difficult to scale to a large environment as it strictly requires a centralized authentication or administration, creating a single point of failure. So you have cross-certified CA topologies like you see here, and this is where you get other certificate authorities in order to transfer that data across. And you can also get hierarchical ones set up there as well. So interoperability between PKI and its supporting services, such as LDAP, which is used for authentication in usernames, passwords, etc. And then X500 directories. It's usually a concern because so many certificate authority vendors have proposed and implemented proprietary solutions. In order to address that interoperability concern, the IETF published the Internet 509 Public Key Infrastructure Certificate Policy and the Certification Processes Framework. And so version 3 of this standard defines the format of a digital certificate and how to make those so that they're interoperable between multiple systems and services. And so now with SSL, those servers are going to use 509 version 3 for website authentication for SSL and TLS protocols, while web browsers are going to use the 509 v3 in order to implement HTTPS client certificates. And IPsec VPNs, they're going to use 509 when certificates can be used as a public key distribution mechanism for the IKE or the Internet Key Exchange RSA-based authentication. User mail agents are going to support mail protection with the SMIME protocol using 509 certificates. And then you have EAP TLS. These are typically switches that can use certificates to authenticate end devices, which can be provided to a central ACS and then be extensible there. So you can use these on switches to authenticate end users instead of, having the proper MAC address or something like that. They actually have to have a certificate on top of that before the switch allows them to pass traffic. So the first step in a central authority authentication procedure is used to secure a copy of the public key. All systems that leverage PKI must have a CA's public key, which is called a self-signed certificate. The CA public key verifies that all certificates issued by the CA are vital for proper operation. And then for many systems, such as web browser, the distribution of CA certificates is handled automatically. It's not something you have to go grab. The web browsers come pre-installed with a set of public root certificates. And therefore, the certificate enrollment process is used by the host system to enroll with a PKI. To do so, a CA certificate are retrieved in band over the network, and therefore the authentication is done out of band using a telephone. This is kind of an older based system here. So only a root certificate or root certificate authority can issue a self-signed certificate that is recognized or verified by other CAs within the PKI. So a system enrolling with PKI contacts CA to request and obtain a digital identity certificate for itself in order to get a CA self-signed certificate. The final stage of this verifies that a CA certificate was authentic and is performed by using an out-of-band method, such as POTS, in order to obtain a fingerprint. Authentication no longer requires the presence of a central authority server, and therefore the user exchanges their certificates using public keys. You can also revoke certificates. This is typical if something, a public key, or I'm sorry, a private key becomes compromised, etc. You can keep a list of revoked certificates and serial numbers that have been invalidated because they've expired. You also have PKI entities that regularly roll the CRL repository in order to receive the current list. And so the CRL is your certificate revocation list. Online Certificate Status Protocol, or OCSP, is a protocol that's used to query that server in order for revocation status of 509 digital certificate. That revocation information is immediately pushed to an online database. You guys will be able to go in and start playing with certificates and checking for man-in-the-middle type of attacks that we did not too long ago. All right, so applications and things that use PKI. These are just some of the more common ways used in SSL, IPsec VPNs, HTTPS, etc. A security analyst must be able to recognize and solve potential problems related to permitting a PKI-related solution on an enterprise network. That increase of SSL or TLS traffic poses a major security threat risk to all enterprises, as the traffic is encrypted and cannot be intercepted and monitored by normal means. And therefore, users can introduce malware or leak confidential information over that SSL connection. And so other SSL related issues may be associated with validating the certificate on a web server. This occurs when the web browsers will display a security warning. And those PKI related issues are associated with other security warnings, including the 509 certificate may specify before or not after dates if it's not within that date range. And you can also have signature validation errors in which a browser cannot validate that signature on the certificate. There's no assurance of that public key in the certificate that's authentic, and therefore the signature validation will fail if the root certificate of the central authority hierarchy is not available in the browser certificate store. And you can kind of watch this. For example, in the Cisco VPN client, you can see that no valid certificates are available in order for authentication. So network monitoring is now going to become more challenging as all your packets are encrypted, and therefore security analysts must be aware of those challenges and address them as best as possible. For instance, when site-to-site VPNs are used, the IPS should be positioned so that it can monitor unencrypted traffic. In other words, it should be on the inside. However, the increased use of HTTPS within an enterprise is introducing new challenges. We must know how to circumvent those particular ones and solve those issues. Things you can do is configure rules to distinguish between SSL and non-SSL traffic, HTTPS and non-HTTPS SSL traffic. That way you can decrypt some of the other ones and not HTTPS. You can enhance security through a server certificate validation using CRLs or OSCP or OCSP, sorry. Implement anti-malware protection and URL filtering of HTTPS content. You can also deploy a Cisco SSL appliance, which is used to decrypt SSL traffic and send it to an intrusion prevention system or an IPS in order to identify risks normally hidden in SSL. So cryptography is always dynamic. It's always changing. Security analysts must maintain a good understanding of cryptography algorithms, as well as operations of being able to investigate cryptography-related security incidents. There's two main ways in which cryptography impacts security investigations. First, the attacks are used to direct specifically targeted the encryption algorithms themselves. After the algorithm has been cracked and the attacker has obtained the key, any encrypted data that's been captured can be decrypted by the attacker and read, thus exposing private data. Secondly, a security investigation is usually affected by data as it can be hidden in plain sight by encrypting it. So the main thing to take away here as a security analyst, you don't have to know exactly how those algorithms work, but you need to be familiar with all the different algorithms and when and why they're used and what are their weak points. And typically the weak point is going to be the message length. What is the key length, etc. And that way, the higher the key that you use, the more encrypted it is. Just know that it's going to, anything can be broken. It's just, is it broken within a time that makes it useful? And so the best way to defeat most of this is with rolling keys. In other words, you should only have keys that are valid for, a fraction of the time it would take to crack. So for example, if you're cracking something with an algorithm that's fairly common, and that, even the world's fastest computer today kind of thing can only crack this in 90 days, well, then you should have a 30-day rolling public key. And therefore you never give them a chance to crack that particular key. In that case, they have to get a hold of your private key in order to even do any good. Same way there, though, with your PKIs, don't keep those around forever. Make sure that those are going to have a rolling key there as well. All right, so what is the main thing with this cryptography module? It's talking about integrity, authentication, confidentiality, using the hash function as a variable block of data. Be familiar with your symmetric encryption algorithms, which are DES, 3DES, and AES. Those are all used when you know a pre-shared key. You also have asymmetric algorithms, such as the public key algorithms, which are used to design or are designed to be used for encryption that is different from from key used for encryption itself. So data confidentiality can also be ensured using asymmetric algorithms. The main one there is going to be RSA, but you also have the public key infrastructure. That process is summarized by using this. Again, public key is used for encryption. Private key is used for decryption. That ensures confidentiality. So when you send your public key out to everybody, you're asking that they encrypt the data that they're going to send you with your public key. That data is sent to you. Only you have your private key to properly decrypt that data in the right fraction. And if it is decryptable, then you know that the data that somebody sent you is authentic because it was encrypted with your public key. If you can't, then you know that something tampered with that data in between. All right. So one last thing that I wanted to go through in this particular module is a lab. You'll have your labs this week, all these ones down here. There's one particular lab that you guys won't see. That's called creating codes. I'm not going to have you guys do this one, but I am going to do it as part of this recording. Just schedule this real fast here. So again, there's not too many more labs in this particular course. This is a pretty heavy load this week, but we're starting to wind down as we start to get towards the skills exam and then the skills challenge, which I hopefully will have set up here within the next week or two. In the background anyway, you guys won't see that one. So for this particular lab, what it's going to do is generating secret codes. This is typically going to be used for VPNs, as we mentioned before. And so we're going to show you how to do that on the Windows client. So you guys can follow along. I'm going to do this in a side-by-side. Okay. So we'll start with the Windows client. And we'll go with the CyberOps user, CyberOps. All right, so inside this toolbox, you're going to have this TNT cryptor. And this will allow you to generate or encrypt different things. Within the text side, we want to click on Encrypt or Decrypt. And this little one here, we'll have another one like meet me at the computer lab after class. And this is just going to be some message. There's a couple different ways that you could play with this. So the first thing they're going to have you do is use AES 128-bit. And you want to have some kind of password in here. We're just going to use CyberOps, such as this one here. And then we click encrypt. And that's going to end up being this little resulted message down below here. If we look at the other options, you have CBCs being used. You can pad things with different protocols and settings. With that result, we could copy that result. And let's see here. If we put this in Notepad. And we're going to save as in our documents folder, encrypted text. Then we're going to go ahead and log out from here. All right, so in this case, they're going to have us log back in as the administrator. That password is also CyberOps. And so you would send this encrypted string across to somebody. Most people would never see that as a message. You would have to know what encryption that's going through there. And so you can have the toolbox come up and then open this up here. We could encrypt. What we want to do is take the message here. We're going to open and copy that in there. So if we open up Notepad, there we go, documents. And notice that you're going to have this document here. Now, it's not going to show up in here, right? Because we are in our administrator documents. So we actually need to follow the trail. So if we go to users, CyberOps user, documents, and we'll see encrypted. We'll copy that information out. Put that on our input here. Make sure that we have this set to the right algorithm and the password, CyberOps. And then we can decrypt that and we'll end up seeing this ending result message that goes over here. So it doesn't look like it's all that cool, but if you actually start playing with some of these, you can see how much more it is. So say we take this same message that we had before and go through here and do this with 256 and then encrypt it. You'll notice that this is a longer key and we can compare that out to this original one here. So notice it's got the same amount of characters that go through there, but it's been flipped even more as it's going through and being encrypted there. What's nice is you can also salt it. So what this is going to do, it's kind of like a password on a password, but if you salt it with some extra data going in there. So if we say like monkey that goes in there and then hit encrypt, now not only do they have this going inside of there, if they were to ever compromise your initial password. So say they realize that your password was CyberOps. If they try to decrypt this, say we come up here and we go to decrypt it, but we don't have the salt, note that we get invalid going across there. So if I go through and decrypt, it says that it has no salt, or it has no way of defining that out. So you would have to try to test and do a decrypt, invalid. If we do encrypt, you would have to try to compare that through. So when you're using cracking programs, which you guys will learn about, a lot of times the way those cracking programs are is it either has a database, which they typically refer to as a rainbow table, in which you have taken every password combination, ran it through the AES algorithm, and then have those result strings for each individual one. Problem is those are fairly ineffective against these type of things, because you have to take a different input. In other words, you're not solving for this password, right? You're solving for the data that's coming in here, and therefore you never know what that result is going to be. So you actually have to encrypt these on the fly, and you basically take data, encrypt it, and then you're going to have to take that password. In other words, you have a known result here. You're going to have to decrypt that by going through a password list, and you can break that. The benefit of using a salt on top of that is it then renders those password lists even less usable, because now you have to have basically a second password or another salt in order to shove this in there. This salt could be the result of another hash, and so you could stack hashes on one another in order to have that be padded through there. You could also play with IV a little bit in order to set that, and that further complicates everything in between there. So, and then obviously you have to have the right mode of operations as well as paddings, and you can play with all these different settings and send things back and forth. Base 64 is another main encryption that's commonly used. You could use different file comparisons, file hasher. So for example, if we go to file hasher and I bring in a file, let's see here, set an Hmac password generate hash. So for, say, this T encryptor, this exe file, we could calculate different hashes, and you'll notice this is the base 64 and the ones in between there. You could also have a password on there on the Hmac side. That's going to further complicate things. You could set this as MD5, and you'll notice that generating these doesn't take too long. You can actually get these different MD5s that go through here. You could also get these MD5s that put it all in uppercase. And then you have the base 64 equivalent of the particular MD5 hash. If you do use Hmac, then you can come over here, and now you can set passwords on top of that in order to encrypt those files. So a lot of times if you're sending files on the internet, remember most of them have MD5 hashes, and that way you could take this file, generate it, and then when you upload that exe file to a website, you could then submit this MD5 hash so that somebody can go through, take the file, and submit that up. And that way they can figure out exactly what the MD5 hash was. If it's different than what you submitted, then somebody has tampered with that file along the way. All right, that ends this particular section. Take a look at it, review it, play with it. You guys can do this lab. I am going to leave it posted in NetLab, but it's not a required lab, and I'll have listed as not required there.